Hi everyone, my name is Lingji Chen. I work for Motional. We are a recently formed joint venture between Hyundai in Korea and Aptiv in the United States. We develop autonomous driving technologies and we are actively hiring. So if you're interested, feel free to contact me. Today, I'm going to talk about how we can handle dependence for certain special likelihood structures. Now, the dependence issue that's sometimes is quite important when we try to decide the data association problem. Here, I have a cartoon drawing. On the top part, I have two previous tracks, and then a new frame of measurements come, and they are denoted by 3 dots. So in determining the measurement to track association, because of the uncertainty in tracks and uncertainty in measurements, any particular dot assigned to any particular box, I would say the likelihood isn't that much different. Here in the cartoon drawing, I'm exaggerating, but you can imagine it's not that different. At least the likelihoods won't be orders of magnitude different. But if we consider them jointly, the two hypotheses, hypo 1, hypo 2, they are okay, they are possible. But the last one, we are saying that the red box on the left now is on the right. So we would consider that a very unlikely hypothesis. So consider them jointly, we would give a very low likelihood for this hypothesis. So in this talk, I'm going to first introduce the basic idea, which is quite simple. And then I will show a simulation. And then I'll talk about the mathematical details. And at the very end, I'll say something about the extended target tracking. Now, why do we often assume independence? Now, in the MHT, multiple hypothesis tracking framework, or more precisely, in the track-oriented MHT framework, we are basically solving an integer linear programming problem. The way we can formulate such a problem is because we assume that when a track is associated with a measurement, that cost is independent of which global hypothesis this association is part of. So that's why we have a vector of costs and we have a selection variable and we solve for that and get the best global hypothesis. In the labeled RFS framework, essentially, we are enumerating child hypotheses. Now, conceptually, we can evaluate the association likelihood between all the measurements and all tracks jointly under one hypothesis. But in practice, when we do the actual computation, we cannot keep in memory all the child hypotheses. We have to do some kind of truncation. We may have a billion candidates. We can only keep top, say, 100. Now, to be able to efficiently get those top 100, we often pose the problem as an assignment problem and run Murty's algorithm to take the top K as our batch of hypotheses to keep in memory and move forward. Here, I'm only focusing on deterministic algorithms. Stochastic algorithms, that's a different story. So it's for practical efficiency that we assume independence. But how do we handle a dependence issue like in the previous example, cartoon example? Here it's easy to see that we can simply take 100 proposed hypotheses, ignoring whether there are not collusions in it. But after we run the Murty's algorithm, get our 100, we can examine each one. And sometimes there is a collision, and we'll drop it. So after that, we may have only a top 80 instead of 100. And we can keep going, get the 100 first, 100 second, and so on and so forth until we have our 100. Now we can extend this slightly. It doesn't have to be 0 or nothing. If the after we propose, the actual likelihood structure guarantees that when you actually evaluate the likelihood, it never increases. It can stay the same or drops. Then we are all set. We can say, okay, we run the Murty's algorithm, solve the assignment problem, get our proposed solutions, and we examine them one by one. Sometimes they stay the same, sometimes they drop, like these two examples. These are just made up numbers for likelihoods. Now, whenever some likelihood stays the same, that provides a certificate for the correctness of the ranking at this level and above. So if by this time we have obtained 100 of them, then we are guaranteed we have obtained the best 100 of them. That's a key. So here I'm showing a very simple simulation. It's a 1D target. The target is a one-dimensional dot. Two targets are traveling on a one-dimensional road. It's a line. So in this graph, I'm showing snapshots at each time instant. So the numbers are measurement IDs. The gray and the green numbers are measurement IDs. The red numbers are track IDs. And I'm running an RFS, labeled RFS. So because it's 1D road, the following car cannot overtake the leading car. So when I do Monte Carlo simulations, because of the noise I injected into the measurement and the tracks estimate, sometimes I will get these invalid results. There will be crossings of these of the two targets. That's because I am assuming independence, but they are actually not. There is this constraint. So if I explicitly try to model the following aspect of it, that's a bit complicated. But if I run the previous algorithm, I'll just throw away those hypotheses that have correlations in it. Then I'll get a result like this. I'll always get valid results like this. So that's solving some dependency issues in this simple tracking problem. Now let's look at some mathematical details. Now the top equation shows the Bayesian formula for the random finite set setting. The focus here is the likelihood term G, that's the global likelihood. That's the likelihood of the set of measurement Z conditioned on the set of tracks X. Now, if we assume independence, then it takes this nice form. It's nicely factored. Each term has only one with only a particular track, and that's why we can formulate a nice assignment problem. But we can extend this slightly. We can add a term lambda, add this factor to depend not only on just one track, but depend on all the tracks. Still, we want the factor form. This enables us to do track update easily, but we can have this lambda term. If the lambda term is such that it's between 0 and 1, then the previously presented proposed and verified algorithm can be applied. You can start with lambda equals 1, giving everyone the benefit of the doubt. And then after you propose and efficiently obtained top candidates, you can evaluate everyone, and the likelihood can only drop down from 1. So these two particular examples, in the correlation likelihood structure, is simple. We have a procedure to decide whether there is or there is not a correlation in this hypothesis, denoted by theta. So it's either lambda is either 0 or 1. So either it's, there's a correlation, we don't want it, or nothing is different from when we assume independence. That's one case. Another case, we would have to modify this individual likelihood term slightly. So J denotes the measurement ID assigned to track labeled L. Now, if it is detected, there's a factor PD, probability of detection there. If it's 0, meaning the track is misdetected, then usually we would put 1 minus PD here. But to put it into the framework with lambda, we would move this term into lambda. So we would say if it's misdetected, we will just give it the benefit of the doubt. We say it's occluded by something, and that's why we don't see it. So we'll put 1 there. But after we obtained the candidate, we actually look at all the tracks involved. We can decide whether it is or it is not actually occluded. If it is not occluded, then the term will go down from 1 to 1 minus PD. This PD, by the way, only models that particular point at that track. For that track, it's not modeling the entire thing. So it's either stays as 1 or it drops from 1 to 1 minus PD. So this would satisfy the previous requirement that lambda is between 0 and 1. That's why this type of occlusion likelihood structure also falls into the category where we can handle the dependence. So basically, individually, we can only model the local detectability, but jointly we can say when it's misdetected, we give it the benefit of the doubt. We assume it's occluded by something, by some other track. And then when we actually evaluate it, we can actually account for whether it is or it is not occluded. And we can do this efficiently. Now, in the paper, I also had a section about the need for better mathematical tools for extended target tracking. Now, what I mean there is that the extended target tracking problem, the space we operate is not just the space of the kinematics augmented by the space of geometry. Here, I'm illustrating my point with a very simple example. Now, the target, let's say the target kinematics has only one state, which is a position, 1D position. And the target geometry has only one dimension, that's the length. Now, if I talk about the joint distribution of two targets, their kinematic states, meaning I'm talking about the joint distribution of the position of target 1 and the position of target 2. The support of this distribution has this shape. It is the plane with the diagonal taken out, and this diagonal has a finite length, has a non-zero length. So the measure is not 0. Unlike in the point target case where the diagonal is taken out, but it has measure 0, it doesn't affect any of the big integral. So that's one example on the left. On the right, if we consider conditional probability distributions, now again, 1D example, the space is position and length. If it's conditioned on one other target, the support takes the shape of the top figure. When it's conditioned on two targets, the shape of the support of this conditional distribution takes the shape of the bottom figure. So here, when we say a Gaussian distribution, what exactly does that mean? And so it may be just my ignorance. Maybe I am not aware of rigorous mathematical tools to deal with these. I'd be happy to learn if they exist. So in summary, we can handle dependence, data association dependence in some special likelihood structures if they satisfy certain conditions. And here are two examples that are described in the paper. Maybe we'll find more in the future.